Hello guys, my name is Balkrishna Srivastava and welcome to Code with BK. So in this video, we write a Java program to check if an integer is a happy number or not. So before we begin, it is a request to please subscribe to my channel because out of 100 viewers, only 2 to 3 are subscribed. More than 95% of my audience is not subscribed and a subscription is very important. So please just subscribe to my channel. And one more thing before we start, I teach coding in Hindi on a separate Code with BK Hindi channel as well. And Code with BK was the first channel I started but I then started getting a lot of requests to teach in Hindi, for which I started a separate channel. So this is a request, if you guys could spare maybe 5 minutes and check out this channel and let me know your reviews about this. Okay, let's go. So we have to check if an integer n is a happy number or not. So let's first understand what is a happy number. So if I have say n equal to 13, I need to check if this is a happy number or not. Happy number is a number which eventually reaches 1 when replaced by the sum of square of each digit. Okay, that is, you have to sum square of each digit. Okay, add them. So this is 1 plus 9, this is 10. Okay, is this 1? No, not yet a happy number. So we can do the same process of adding the squares of digits. Okay, so 1 square plus 0 square gives you 1 plus 0 gives you 1. Is this 1? Yes, this is a happy number. Okay, because eventually the sum of digit squares lead to 1. Okay, let's take a case which is not a happy number. So let's take 4. So 4 square is 16. Okay, 16 then has 1 square plus 6 square. This has 1 plus 36 is 37. Okay, have we reached 1 here? No. 1 here? No. Okay, so we further calculate 3 square plus 7 square. This is 9 plus 49. So this is 58. Okay, we further calculate 5 square plus 8 square. This is 25 plus 64. Okay, this is 89. We further calculate the sum of squares, 8 square plus 9 square. This is 64 plus 81. This is 145. We further calculate 1 square plus 4 square plus 5 square. This is 1 plus 16 plus 25. So this is 42. We further calculate the sum. We say 4 square plus 2 square. It is 16 plus 4, 20. We further calculate 2 square plus 0 square. We get 4. So we started at 4. We are at 4 again. Okay, so this is not a happy number because this cycle will keep on continuing. Okay, because after 4 you will get 16 again and then 37 and again you will reach at 4 and the cycle continues. Okay, so detecting a cycle is how we check if an integer n is not a happy number. Okay, if it reaches 1, it is a happy number. If you are having a cycle, okay, because it continuously keeps generating numbers, we know this is not a happy number. Okay, so I'm going to write a function. Okay, static boolean is happy number, takes an integer n, returns true if this integer n is a happy number, returns false if this n is not a happy number. Okay, so start an infinite loop. Okay, so while true. Okay, the reason for starting an infinite loop is because I want to keep continuing this step of calculating the sum of digit squares. Okay, if I find somewhere 1 as digit square sum, I return true. If I detect a cycle, I return false. Okay, otherwise I keep generating the values. Okay, so what you have to do is calculate the sum of digit squares. Okay, so in order to calculate the sum of digit squares, suppose if I want to calculate the sum of digit squares of 13, I convert this to a corresponding string. Okay, then I iterate the string. I pick up each character in each iteration. So I get 1 in first iteration, 3 in next iteration. In each iteration, I get the corresponding integer value, which I square and add to get the digit square sum. Okay, so I convert the integer to string. Okay, so if my n was 13, my n str would be string form of 13. Okay, and in Java we are allowed to do this. Okay, we can append a string to an integer. Okay, then we need to calculate the digit square sum, int digit square sum, which starts with 0. Okay, so I iterate this string nstr dot length I plus plus. Okay, I get the ith character as nstr.caret I. Okay, so if n is equal to 13 again, nstr is string 13, then we have ch as 1 in the first iteration, 3 in the second iteration. Okay, we get the digit as ch minus 0, the standard way to extract the digit from a character that contains a digit. So this is actually subtracting the corresponding ASCII values. ASCII value of 0 is 48, ASCII value of 1 is 49, ASCII value of 2 is 50. Okay, so ASCII values of 0 to 9 are continuous. So when you want to say extract 2 out of this ch that stores the character 2, you do ch minus 0, which is basically 2 minus 0, which is 50 minus 48. Behind the scenes, the corresponding ASCII values are being subtracted. 50 minus 48 gives you 2. So you get the digit 2 out of this character that stores digit 2. Okay, then you calculate digit square, which is digit into digit. Okay, digit. You can use math.pow as well. You can say you can either use this or you can say math.pow digit to the power 2. Okay, but since this runs a double, you have to typecast this explicitly to an int. Okay, you do this or you do this. Okay, and then finally you add this digit square to the digit square sum. Okay, so the process of calculating the sum of digit squares is done. Now check if digit square sum is 1. Okay, if digit square sum is 1, we have reached 1, so we return true. Okay, else if my digit square sum is the value that we started from, we return false. Okay, we detect a cycle. Okay, this is not very efficient. This does not work in all cases. We'll see in a moment. Okay, else if it is not 1 and it is not a cycle, that we have not found a true or a false case, in that case we set n to digit square sum. Okay, why do we do this? Because in this case, for example, n starts with 4. Okay, and we get digit square sum as 16. Okay, then in the next iteration this has to become n, so that this is the next digit square sum. So we set n to this square sum. Okay, if it is not a true and not a false case. Okay, all right, so this is your method to check for happy number. Let's just test this for 13. This is out. Okay, is 13 a happy number? Okay, is happy number, you pass 13, we should get true. We get true, which is correct. Okay, let's try to find out happy numbers between 1 to 100. So I comment this out. Okay, I say for int I equal to 1 and less than equal to 100, I plus plus if is happy number I. If I is a happy number, I print this. Okay, system.out.println. Okay, I plus is a happy number. Exclamation mark, sorry. Okay, let's run this. So we have 1, and for the other cases this red light is on, that is we are into an infinite loop, that is this condition is continuously running. We are not getting return false or return true. The values are being continuously generated. Okay, now the problem is, okay, first, since we are continuously changing the value of n, okay, n was this, then n became this, then n will become this, then n will become this. Okay, so this comparison has to be with the original value of n, which I store in a separate variable n copy, because after the first iteration the value of n is lost, the original value of n is lost, and we want to compare the digit square sum with the original value of n. Okay, do we have any improvement in the performance? No, still the red light on. The other major optimization is, you say if digit square sum is 4, that is somewhere in this sequence of generating continuous values of digit square sums, you find a 4. It means it is not a happy number, because you are going to end up with 4 again and the cycle continues. So finding a 4 is basically detecting a cycle, which we are doing in a separate case. Once we do this, we see there is a clear change in performance and we get all our happy numbers. Okay, and the critical thing here is this is not much of a code. Okay, the code remains almost the same. The optimization here is mostly maths based. I mean, we did the work apart from our coding. What cases will surely return false. Okay, so coding a problem also involves how much can you solve the problem outside the coding, right? So you can optimize your program as much as possible. Okay, and this things like this, minor things like this are very handy in your competitive coding. We are trying to solve a problem as fast as possible. Okay, so my happy number method works. Okay, all right, there are a couple of things more I want to tell here. First is, when you look for the solution online, they find this return false case in a separate way. That is, in order to detect a cycle, they have a set of values in which they are continuously adding digit square sum. Okay, whatever sum is being generated, it is being added to a set of values. Okay, and in any next iteration, if a digit square sum generated is found in this set of values, it means it was previously generated. It means we have detected a cycle. Okay, and we try to solve the problem using that as well. So I am going to write is happy number 2. We make this 1. Okay, we make this 1 as well. Okay, all right, so the process remains the same. Okay, we just create a set. So I will use inbuilt set of Java, which is a hash set. It is supposed to store integers, so I'll say set equal to new hash set. Okay, every time a digit square sum is calculated, I am going to add digit square sum to the set. So set dot add digit square sum. Okay, and my false condition is going to change to, okay, finding digit square sum in the set already. Okay, so if my set contains digit square sum, okay, I return false. All right, so in every iteration we are generating this value digit square sum of square of digits. If it is found in the set, that is it was generated in some previous iteration, I return false because they detected a cycle. Else we update n and add digit square sum to set. We are not adding it here because if I add digit square sum here, okay, it is added to the set, and in the very next if else if I'm checking if the set contains. Okay, so I'm adding here, I'm checking here. So this is always going to be true because I'm in the same iteration. I'm adding the same value, I'm checking for the same value. So in order to check if digit square sum is in the set or not, we add this digit square sum before the next iteration. Okay, not in the same iteration. Okay, this iteration completes here. So before the next iteration, we add digit squares. Okay. All right, we don't need n copy, and is happy number 2 should give you the same output. Okay, gives you the same output. We can test happy number 1 for 1000. Okay, we can test happy number for 10,000. Okay, we can test happy number for 10 to the power 5. Okay, all right. So the other way to check for happy number 2 is if is happy number 2 not equal to is happy number 1. That is, if both the functions return different values, it means I have an error. This is out. I will print error. Okay, and I will comment this out because there will be a lot of cases for happy numbers. If I don't get any error and I just simply get done, it means happy numbers are being checked correctly by both the methods. Okay, so I get done. Okay, for 1 to 10 to the power 5. So happy number 1, happy number 2, both approaches work correctly. Okay, so you can also check which method is faster by timing this. The second method is going to be a little slower, although both are fast, but comparatively this is going to be slower because to a set you are adding and you are searching. Okay, that takes a little more extra time because otherwise this loop, this while loop, is exactly the same as in the previous case. Okay, so happy number 2 will take a little more time. So what I can do is I do this. Okay, if is happy number 1, okay, I check. Okay, I don't do anything. Okay, pass. Okay, similarly, and to time this I say long start is system dot current time milliseconds, long end. Okay, I'll say sys out. Time taken is by 1 is plus end minus start plus milliseconds. Okay, and similarly for the second case, I check for happy number using method 2. I start before the loop, I end after the loop, and I say time taken by 2 now is start minus end. Okay, end minus start, sorry. Okay, all right, I just comment this out. So I get just 2 time outputs. Okay, the time taken by first method, time taken by second method. Okay, so second one is slower. If I make this 10 to power 4 for both the cases, 10 to power 4, right? Second one is still slower, but you really cannot test the runtime with lesser number of iterations. Okay, so let's make this 10 to power 6. Okay, so you can see the second one is slower again for 10 to power 7. Okay, second one is taking 2 seconds and the first one is taking almost 1 second. Okay, second one is slower as well. Okay, all right, so this was the solution to this problem and I hope this was helpful. We used loops iteration in this case. If you want a recursive solution, please let me know in the comments. I'll try to add that as well. So please let me know in the comments if there is a doubt, there's a part you do not understand. I always try to answer all your comments. And you can also let me know in the comments if there is a question you want to solve or if there's a concept you want to discuss. So please like this video, subscribe to my channel, and thank you for watching.